So picking up where we left off in the last video, this video is going to kind of cover a couple more transformations that I mentioned, specifically the contraction slash dilation transformation, and then the rotation transformations. If you go in the textbook, there is a huge list of a whole bunch of different matrices that do a whole bunch of different things, and you don't need to memorize all of them. To be honest, I personally, and this is just my personal take, don't care that people, are able to recognize immediately that, certain matrices do certain things. I think that the basic ones that I'm showing you in the last video and in this video are good to be aware of. But for the greater purpose, we're just kind of learning about these things, and they exist, and they're tools that we could use for particular instances. So we're going to do 3 examples here. The first is contraction or dilation. This is usually the absolute easiest one. And a transformation that is a contraction or dilation basically just means that our matrix, instead of just being the identity matrix, which this thing right here, we call this the identity matrix. And the identity matrix is essentially the equivalent of the number 1 in numbers. So, that's like a 2x2 identity matrix. The 3x3 identity looks like this, and it's basically like the goals that we would want to get if we were trying to get a matrix in RREF, where we have a 1 in every pivot, and that every single column has a pivot, and things are nice and dandy. So the identity basically doesn't do anything to a vector, right? If I were to take a random 2x1 vector here, so x1, x2, something from R2, or if I were to take a random vector x1, x2, x3 from R3 here, this would just give me back the same vector. So nothing too exciting is going to happen here, and you should do this to kind of verify that happens. But a contraction or a dilation would be if these numbers were something other than 1. So for instance, if they're all the number 3, then this would be a dilation, because what it's going to do is it's going to put a 3 in front of all of these when we finish, which basically means that we have 3 times the vector that originally went in to the transformation, right? Remember, this is the input. This is kind of like our B vector that we get out. And so this is a dilation. A contraction would be if these numbers were fractional. Okay, that is contraction dilation. I'm not being super rigorous with it because this one, it takes the least amount of thinking to think about. Another one that is going to take a little bit more effort is a rotation matrix. So again, for the sake of just having nice, easy examples to kind of wrap our brains around things, we're going to be doing R2. So for example, come up with the matrix A for the transformation, or the linear transformation, but the transformation, I'll specify linear transformation. For the linear transformation, T that maps from R2 to R2, that's defined by T of X is equal to AX. So come up with the matrix A that rotates a vector 90 degrees counterclockwise. And remember in the last video, I said that, to come up with the matrix A, all we need to know is what is happening to the standard basis vectors. And so what I would suggest to complete this problem is simply to draw a little sketch. And on this sketch, I would draw the standard basis vectors as they start. So the standard basis vectors, of course, are going to be 1, 0, and 0, 1. And what I'm interested in is, where do they end up after you rotate them 90 degrees? Well, the first vector, E1, ends up here. So it ends up actually, at 0, 1. And then the second vector, the second standard basis vector, would end up down here. And that would end up at -1, 0. And so it turns out that this matrix A that we're looking for, that's going to rotate a vector by 90 degrees, this matrix A is just going to equal, it's the image, remember that it's T of the first standard basis vector, and then it's what happens to the second standard basis vector. And so we know that the image of the first one is just 0, 1, and the image of the second one is -1, 0. And, sure enough, maybe we can kind of convince ourselves that it worked by, say now that we have like our answer, we could say, consider, or not even consider, let's just say evaluate T of, let's just come up with a vector like 1/2 √3 over 2. Okay, so that vector lives up here. It's at pi over 3 radians. So this is 1/2 √3 over 2. And we want to know where would it end up if we rotated it, by 90 degrees. Now there's ways we could do this just using good old-fashioned pre-calculus, but since we want to get some practice here, this is going to be, we just take the matrix 0, -1, 1, 0, and multiply it by 1/2 √3 over 2. And if we do this, we're going to get, I believe for the first entry, we're going to get -√3 over 2. And then for the y entry, we get 1/2. And this should make sense because if we rotate this 90 degrees, right, if we're located at 60 degrees for starting, or pi over 3 radians, then we're going to end up at 150 degrees, which is going to be 2 pi over 3, no, not 2 pi over 3, what am I saying? If we're talking about being at pi over 3 and we add pi over 2 to that, that's going to end up put us at 5 pi over 6 radians, which leaves us with a reference angle of 30 degrees. And sure enough, this side of this triangle is 1/2, this side is -√3 over 2, so the coordinates would be -√3 over 2, comma 1/2. So this is our first example of basically coming up with a transformation where we weren't given the image of the standard basis vectors or really anything to go off of, and we had to build the transformation all on our own. So a slightly spicier version of this for maybe our last example of what we're doing, a slightly different version of this would be to say, create, let's create a matrix A for the transformation T going from R2 to R2, such that, I'm just going to word this one differently just to kind of build some kind of fluency, if you will. So create a matrix A for this linear transformation T that maps us from R2 to R2 such that, X gets mapped to AX, where we take a vector X, and rotate it, theta degrees counterclockwise. So this one is a little bit more interesting to think about because, again, the goal is to figure out what happens to the standard basis vectors. So we're going to draw a picture. But this time, I'm not giving you that it's exactly 90 degrees. We're starting with our standard basis vectors of 1, 0, and we're starting with this one here at 0, 1. But now we're going to rotate some amount theta, and we're going to end up at some new vector. And the idea is that I don't know what this vector is. And similarly, we're going to rotate this one by the same amount, and we are going to end up equivalently, at some new vector that we don't know what it is, but at the very least, we know that we went the same angle theta. Okay, and so the question is, where are these going to end up? Okay, so what we might notice here is that because we don't know what the angle is, the answer is that it depends where we're going to end up. But hopefully you might recall that 1, 0 lies on the unit circle. And so, since we're doing rotations of sort, it may be better to think that if I rotate this vector by some angle theta, it might be better to refer to the coordinates here, right? This isn't so bad to think that, courtesy of our pre-calculus knowledge, that our new vector is going to be located at cosine of theta and sine of theta. Now that's easy for the vector 1, 0. And so the question is, what's going to happen if we rotate the second basis vector, the 0, 1? Well, as we rotate that one counterclockwise by theta as well, well, these vectors are going to be kind of mirrored from each other. And so the only thing that's going to be different here is that since we're starting now at 0, 1, this new vector that we're going to get is going to be negative sine in the x direction, negative sine theta, and cosine of theta in the y direction. Now, how come that is? Well, maybe I'll make this drawing a little more accurate to make it a little more sense. So since they're rotating the same exact amount, these are going to be kind of at 90 degrees of each other. So these are going to be 90 degrees from each other. This is going to be theta, right? And so basically these triangles are essentially the same triangle, with the exception being that, if this was sine theta before, well, that side right there is now here. This is what sine theta was before, but we're in the negative direction, so it's going to be negative. And likewise, if this was cosine theta before, then that's going to make this height right here cosine of theta as well, because this angle theta, that's the same as here if I put a theta there, by similar triangles and things of that nature. So this example is kind of like just an in-your-face, you would never have thought to do this on your own, but it's in the textbook explained if you want to really kind of dive into it a little bit. And what this tells us is that our matrix A consists not of numbers this time, it consists of these functions: cosine of theta, sine theta, and negative sine theta, and cosine theta. And so now, for instance, if I had said, okay, this is the matrix that represents the linear transformation for rotation of an angle by theta, what if I want theta to be 90 degrees? Well, if theta is 90 degrees, aka pi over 2 radians, right, what would we get? Well, cosine of pi over 2, what's that? Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So that means there's going to be a negative 1, and that's going to be a 0. And hopefully this looks very familiar to what we did earlier, where we got the matrix 0, 1, negative 1, and 0. We did that already. And we did that by just kind of going the long way of doing, by figuring out, where 1, 0, and 0, 1 go when we rotate by 90 degrees. This is like the general form of how we would do it if we wanted to rotate by any angle theta that we wanted to come up with. So that's going to do it for this video. This is just this one's a little bit of a shorter video, just covering a couple of the other very common transformations. I think that covers everything for here. We just have one more video left in this week, so go on and go check it out.